Thank you so much for attending this presentation. My name is Bo Jian, and I'm here to present our work DietCode, which is on automatic code generation for dynamic tensor programs. Before diving into the details of DietCode, let us first do a quick review of the current autoscheduler design, which starts with a user supplying an operator specification and a static shape description. Based on the provided information, the autoscheduler automatically constructs a search space that includes all the schedules under consideration. However, the key challenge is that an operator can in theory have infinitely many possible schedules. As an example, consider the compute as is shown on the slide. Imagine that we are about to apply the loop telling transformation to the loop structure. As you can notice as well, even with such a simple transformation, there can be infinitely many possible telling candidates, as is shown on the slide. To limit the search space, one of the solutions that is commonly adopted is to circumscribe the telling candidates to those that are perfect factors. Because the perfect factors are dependent on the loop extent, we hence name this approach shape-dependent search space construction. The additional benefit of this approach is that it can also avoid the necessity of introducing other boundary checks in the loop body. To efficiently search through the search space, the autoscheduler introduces a complete program cost model that can accurately predict the performance of each schedule. During the learning process, the autoscheduler uses the cost model that is constantly updated using real hardware measurements to guide the search in the shape-dependent search space, and finally deliver a high-performance program. However, we do notice that there are several challenges faced with the current autoscheduler design, with the first one being that it's hard to share the schedules across different shapes of the same operator. Consider the loop telling examples that we have previously. Imagine that the outer loop extent has been changed from 50 to, say, 49. With this a simple change, the telling candidates have been reduced to a single element set 7, which does not have any intersection with all the factors of 50. The fact that it is hard to share schedules under the shape-dependent search space construction further implies that it is extremely challenging to autoschedule dynamic shape workloads. Assuming that we have a workload whose shapes are dynamic at compile time, in order to autoschedule for such a workload, we need to search for each shape instance of the workload, as is shown on the right-hand side of the slide, which is clearly inefficient. The second challenge the current autoscheduler is facing is that it can deliver suboptimal performance for not considering non-perfect candidates. Still the same telling example, clearly the current set with a single candidate is too limited, as telling candidates 2, 3, etc. are also viable, and they might deliver better performance compared with 7. Although it is correct that extra other boundary checks have now to be injected inside the loop body for the program to be correct, we observe that the performance overhead of those other boundary checks can be negligible with the local padding code generation optimization technique, a technique that pads tensor locally by the size of the local workspace. To address those challenges, we propose DietCode, a new autoscheduler framework that efficiently supports dynamic shape workloads. Due to the time limitation, in this presentation, we mainly focus on 2 key ideas or submodules of DietCode, namely the shape generic search space and the microkernel-based cost model. Our first key idea, shape generic search space, constructs a search space that is composed of microkernels. Each microkernel does a tile of the entire compute and can be ported to all shapes of the same operator. As an example, on the right-hand side of the slide, we are illustrating how the microkernel dense 128 by 128 can be used to realize the compute 1024 times 2304 by replicating itself 8 times 18 times along the spatial dimensions. The microkernels are sampled mostly from the hardware constraints instead of the shape factors. Hence, they form a shape generic search space. Our second key idea, microkernel-based cost model, is from the observation that the existing cost model, if trained on one shape, can be inaccurate on other shapes. As we can see from the right-hand side of the slide, as we vary the shape of the workload, the existing cost model is unable to capture the change in compute throughput. We further notice, however, that the compute throughputs exhibit predictable linear trend with respect to the shape dimensions. This therefore motivates us to build a new cost model that can be decomposed into two components. A trainable microkernel cost that is modeled using XGBoost, and an analytical spatial generalization cost that is modeled using a linear function. With those two key ideas, we further devised a new interface of DietCode to better support dynamic shape workloads. The new interface allows users to define dynamic shape variables and their instances, pass those variables and instances to the workload function, and optionally assign weight to each shape instance. To test the effectiveness of DietCode, we evaluate our hardware platform equipped with a more than Tesla T4 GPU, CUDA 11.3 and CUDA 8.3. We use DietCode to auto-schedule the dense layers extracted from the BERT model, which is a state-of-the-art language modeling application. The sequence length that we use is uniformly sampled within the range from 1 to 128. We observe that with those sampled sequence lengths, DietCode delivers on average 30% better than Answer, the current auto-scheduler design in PDM in terms of performance, and 5% better than the Cup-Glass Wonder library. Furthermore, since DietCode only needs to auto-schedule once and for all shape instances, its auto-scheduling time is 5.6 times less than Answer. To make it even more exciting, DietCode also supports workloads with multiple dynamic axes. We auto-schedule the batched matrix multiply layers extracted from the BERT model with a dynamic spatial axis and a dynamic axis being a dynamic reduction axis. As we can see from the result, across all the sequence lengths evaluated, DietCode delivers an average 24% performance better than Answer and 15% performance better than the Wonder library. These results indicate that DietCode is a practical auto-scheduler for dynamic shape workloads. In this presentation, we present DietCode, an auto-scheduler for dynamic shape workloads. DietCode is based on two key ideas: constructing a shape generic search space that is composed of microkernels, and using the microkernel-based cost model that consists of a trainable microkernel cost and an analytical spatial generalization cost. Our evaluation of DietCode shows that it only needs to auto-schedule once and for all shape instances, leading to a large reduction in the auto-scheduling time. Furthermore, it can deliver performance by up to 30% better than Answer and 15% better than the Wonder library on a modern GPU. We are currently working on integrating DietCode as part of the TBM main branch. Thanks again for attending this presentation.